In the medical industry, there is a demand to measure vitals in a non-invasive and convenient way, particularly measuring hydration in elderly patients on several medications. Currently, to measure patient hydration level, a doctor takes blood samples, a fairly invasive procedure. To measure respiration rate, patient breaths are counted manually. This method can be inaccurate if the patient knows that their breathing rate is being measured. Over the last 2 semesters, our senior design team has worked to address this need by designing a device to measure body hydration level and respiration rate on a wireless, flexible patch.
Our device has 4 major components: a hydration sensor, respiration sensor, Bluetooth module, and phone application. Our hydration sensor is made up of a laser diode that transmits light into the skin at the absorption wavelength of water, and a photodiode which receives the reflected light. The photodiode transforms the light received into a voltage value corresponding to body hydration level. The respiration sensor implements photoplethysmography with the PPG sensor. Using the heart rate signal from the PPG, we determine the patient's respiration rate. The data from these sensors is sent to the Bluetooth module, which includes an Arduino for information processing and a Bluetooth chip which conveniently passes the raw data to a smartphone. The phone will use an application to display the data in an intuitive, graphical format. Heart rate is measured using a PPG, which implements photoplethysmography to illuminate skin and measure the change in light absorbance. We started with sample code from the Arduino library to detect a heart rate signal, and we tested the accuracy of our sensor against an Apple Watch.
To measure respiration rate, we attempted to isolate a near DC component of the heart rate signal produced by the PPG. In this demo, you see a patient breathe at a specific rate while wearing the respiration rate sensor on her fingertip. The raw data is read in through a serial terminal. We reduce the noise in the data by processing it in MATLAB. The data is smoothed using an averaging filter algorithm. The filtered signal is plotted for readability. Research is still underway to improve our respiration rate sensor. Our team developed an optics-based device to measure hydration levels in a patient. From our research, we discovered that water absorbs light at a wavelength of 970 nanometers. To meet budget requirements, we chose to use a laser diode which emits light at 980 nanometers into the skin, and a 980 nanometer peak photodiode to receive the light reflected out of the skin. We hypothesized that the voltage received by the photodiode should decrease as more water is present in the tissue because water will absorb more of the 980 nanometer light. To test our hypothesis, we first tried the laser diode and photodiode on our wrist. After getting noisy results, we tried transmitting light through the earlobe. Here the motion artifact was too high. To remove some of the confounding variables such as motion, we performed experiments using water and isopropyl alcohol in beakers. When changing the concentration of water in our IPA and water mixture, we noticed a correlation present between the voltage values we read and the amount of water in the mixture. While further investigation is required, our preliminary results are promising. We integrated our sensors onto a flexible substrate called Captain. After creating circuit designs in AutoCAD, we printed them directly onto the Captain in silver ink using the Dymatics inkjet printer shown here. We placed the components using a 3-phase stage, microscope, and thermally cured silver epoxy. Here you can see the first revision of our full design. To display our vital sign measurements, our team created an Android application written in Java with the help of Android Studio. The smartphone application connects to the Bluetooth device to receive data. The user can choose which vital sign they want to measure, and after taking measurements, a graph is generated on the smartphone screen. While taking measurements, the app displays a number corresponding to the patient's heart rate and graphical preliminary output of our respiration rate and body hydration level sensors.
Oh, I didn't know you wanted me to be serious.
I was just giving you bloopers.
Oh, good.